Welcome back to the class on Neuronal Dynamics. I hope that each of you has spent 10 or 15 minutes with the exercises 1.2. All those who had no problems solving those exercises can skip over this set of slides and go directly to lesson 1.3. For the others, I've prepared here some additional information just to remind you of the properties of one-dimensional linear differential equations. So this is the kind of equations we have. We have here a linear differential equation, and we want to apply some arbitrary input current. And we are interested in calculating the response, the voltage U of t. And as a first step, we are going to do this for a step current. So here is the step current. How can we proceed? So at beginning, the step current is 0, which means this current here is 0. And now we can take two different approaches. Let's take the mathematical approach first. The mathematical approach is to look for a stationary solution, a fixed point defined as a derivative which vanishes. The udt equals 0. Now if the udt is equal 0, then we are in the case that I equals 0. That means 0 is equal to u minus u rest, or u is equal to u rest. U rest is the resting potential. Say it's here, u rest. So we know that while the current is 0, u equal u rest is a solution. So supposing that we started at 0 at u rest, there's no need that the thing change, that the evolution changes, so we stay fixed at the level u rest. Now we apply the step current. After the switch, the step current has a new value, I1. So let's do the same thing again. We look for a fixed point, but now I is equal to I1. Therefore, we have 0 equals u minus u rest plus r times I0, or u is equal to u rest plus r times I0. So I know that for constant input, there exists a solution for the voltage which is constant as well. Let me draw it like this here. So this is my voltage, which I call now U1 to keep things simple. So this is U1. U1 is the stationary state, and it will be reached after some time. But it does take some time to reach this new stationary state. I told you earlier that all differential equations, linear differential equations, one-dimensional linear differential equations, are characterized by a time constant. Here's my time constant tau. The solution always is exponential. The solution of a one-dimensional linear differential equation is an exponential. So, supposing that this is the new solution and we start from here, we have to fit in some exponential to connect the two solutions. And here is how you can construct this. So we know that before the switch in this regime, u is equal to u rest. Afterwards, it has a new value u1, which is u rest plus r times I0. So the new value r times I0 will not be approached immediately, but exponentially. So let's try this. E to the minus t over tau. So the result now is that it approaches exponentially this new value u rest plus r times I0, u rest plus r times I0, and this gives exactly this kind of curve, an exponential approach. You can check that this is indeed a solution of the differential equation by taking the derivative. So let's take the derivative. d dtu is u rest, has no derivative, it's a constant. R times I0 is also r times I0 times 1 is also a constant. So I have r times I0, derivative of this exponential gives me a 1 over tau e to the minus t over tau. We have to compare this with the differential equation up here. So I have u minus u rest, u of t minus u rest is r times I0 minus r times I0 e to the minus t over tau. U of t is this. I subtract u rest. I have those terms, which I write as two terms. Now you see that this is indeed, let's go back to differential equation. This is indeed the correct solution because I can write this as u minus u rest plus r times I0. Therefore, I am okay. So what we have found is that the solution to a step current input is the resting potential plus a change, and the change is not step-like, but it's approached, the new value is approached exponentially, so the solution for the step current indeed looks like this. Now let's continue and look at the case of a short current pulse. If there's a short current pulse, then it's not going to continue because the current stops. So at this point here, it's going down again to the new value. I'm interested in calculating this new value here. The moment when it reaches the maximum, the moment when the current stops and returns back to zero. So if this is t0, then this point is t0 plus delta, where delta is the duration of the current pulse. So this is the solution which we have found before. Now let's evaluate this solution at t0 plus delta at this point in time. So u at t0 plus delta is u rest plus r times I0 1 minus e, and now evaluate the time t at t0 plus delta, so I have here minus delta over tau. Now suppose that delta is really short. Suppose that delta is much shorter than the time constant. That's the condition that I've written down here. Delta defined as t minus t0 is much shorter than tau. That's sort of the end of the pulse. Delta much shorter than tau. Now I can use the Taylor expansion of an exponential. So the Taylor expansion of the exponential is 1 plus x plus 1/2 x squared and so forth. So x is small. X is delta over tau in my case. So let's write this down. I have u rest plus r times I0. The first term of the exponential is 1. It kills this one here. The next term is x, which is delta over tau, plus other terms, which we are going to neglect. Now remember that we defined the time constant tau as r times c. Tau is the time constant of the circuit with a resistance R and a capacity C. I insert tau in this expression here, and I get u rest plus I0 delta over C. Tau is RC, the R is cancelled. Now, what does this tell us? Well, I've here the capacity C, I've here my current I0. This current I0 is applied for duration delta. That's the duration delta. Therefore, I0 times delta is the surface under the pulse, or the charge. I can write this as u rest plus q over c, where q is the charge deposited by my current pulse. And now you see what's going to happen if I keep the charge the same but make the pulse shorter and shorter. So let's now consider a pulse which is twice as high but half as long. It has the same charge. The rise will be faster. The rise will be like this, but it will essentially stop at the same value. If I make the pulse even shorter but keep the charge the same, in the end I will have a jump to the new value, and this distance here is just the charge over c. So this is the mathematical approach. We use a Taylor expansion. Now let's go back at a more physical interpretation. For a more physical interpretation, we can look at the current and say, at the circuit, and we say, I deposit a current for a very short time. Now, if it's for a short time, the current does not have the time to go through the resistor. Instead, the current will basically just go on the capacity. That means if I have a very short current pulse, this short current pulse deposits charge on the capacitor. But if I deposit a charge Q on the capacitor, then I have a change in voltage which corresponds to Q over C. So in summary, a short current pulse that's made really short deposits a charge, Q, in a very short time, and the membrane potential will, at time t0, simply jump to a new value, and afterwards it's just, there's no current anymore. The current is again 0, so you just have an exponential decay back to the resting value. And the jump size is Q over C. Mathematically, the fact that we have a very short current pulse, infinitely short current pulse, that deposits a fixed amount of charge, mathematically this effect is described by the so-called Dirac delta function, which needs to be integrated to make sense. Physically, it has its meaning because of the Taylor expansion. We see that whatever the duration of the pulse, it's short enough, it no longer matters. The jump is by an amount Q over C. So the elegance of the Dirac delta function is that you don't need to work with short current pulses of finite duration. We can take the limit of a very short pulse and then forget the transient and just say it corresponds to a jump. This is a little bit like working with a somewhat lower time resolution. If your current pulse is shorter than the time resolution at which you look at the time course of the membrane potential, then what appears is just a jump. In a physical situation, if you were to zoom in and say, well, the pulse in the end does have some finite width, it's very short, but still finite, then it would not be a direct jump, but it would still have a tiny little slope to the right. The mathematical abstraction gives us a lot of ease of talking about solutions of linear differential equations and other differential equations as well. So now we know that a single pulse leads to a jump of the membrane potential. So if I have a single current pulse here, then the response of the membrane potential will be a jump and it will go exponentially back to the resting value. Now suppose that I have more pulses. Suppose I have another pulse here. So this pulse will also cause a change, a jump in the membrane potential, and the jump will be by the same amount. This is a linear differential equation. The solutions, the elementary solutions, add up linearly. Now suppose that I have many more current pulses of different amplitudes. Each one will make its little contribution. And in the end, I can sum up all the contributions of the different pulses and say, well, what's the response at time t? The response is the response of the first pulse, plus the response to the second pulse, plus the response to the third pulse, plus the response to the fourth pulse and the fifth pulse, and so on. And the net result, u of t, is the sum of all those responses. Now mathematically, you can now consider the situation where at each moment in time you have a different current pulse coming in, and this is the current pulse at some time t prime, and you ask what's the contribution of this pulse to the voltage at time t? Well, the contribution of this pulse at t prime was biggest here, but then it has decayed exponentially. So its relative weight is less than a pulse who came in here and still has a strong contribution. Now, interestingly, this is the solution to the linear differential equation for arbitrary time-dependent input current. And what you have here inside the integral is just the response to a single pulse. That means once you have constructed the impulse response function, you have also at hand the general solution of the differential equation. Technically, this is also called the Green's function of the equation. So, once we have this impulse response function, we know the general solution of the differential equation. The assumption here is that the input current started a long, long time back in the past. The situation is somewhat different if the whole current injection starts at a fixed time t0. So suppose We don't know what happened in the past, but what we do know is at time t0, current injection starts, and it starts at a new value, u of t0. For some reason, say we have measured the voltage, we know at time t0 the voltage was here. The resting potential is somewhere here. Now you have two contributions. You have this part here with the Green's function or the impulse response function, and you have the effect of the initial condition. At the start, we know we have a value u of t0, and this contribution will, this difference here, will decay exponentially. So we need to add an extra t minus t0 over tau for this contribution. It will go down with the membrane time constant tau. Now, the additional current, which starts here, will make an additional contribution to the membrane potential, which I can calculate by this term here. The total voltage is the exponentially decaying pulse caused by the initial condition plus the contribution of the input current convolved with the Green's function. A linear differential equation, this linear differential equation can be solved for arbitrary time-dependent input. We can write down the general solution for arbitrary time-dependent input. Particularly interesting cases in the context of neuroscience are indeed the step current and the short pulse current. So, if you have problems with these kind of differential equations, please work this out for yourself. It's important that you are at ease with linear differential equations. We will need that throughout the class at many occasions. And we have also prepared additional exercises for you so that you can check whether you are at ease now with these kind of linear differential equations in one dimension. And now we can move on to lesson 1.3.